Hello everyone, this is Huidong Liu.
This is Boyu Wang. Today we'll talk about our work, distribution matching for crowd counting. This is joint work with Dimitri Samaras and Minghui. Crowd counting is to estimate the number of people in an image. It is an important research problem with various applications in many domains, including journalism and surveillance. It is a challenge task due to huge variations of crowd densities. In most datasets, each person is annotated by a single dot on their head. State-of-art method treat crowd counting as a density map estimation problem. The network predicts a 2D crowd density map. The total size of a crowd can be estimated by summing up the density map. The prediction map is dense, while the ground truth map is sparse. During training, how to measure the discrepancy between these two different density maps is important. Simply computing the pixel-wise loss between the sparse annotation and predicted density map does not work well. The loss is highly sensitive to the exact head location and heavily unbalanced between zeros and ones due to the sparsity of the annotation map. One approach to alleviate this problem is to turn each annotated dot into a Gaussian blob, such that the ground truth is more balanced. The network is trained to minimize the pixel-wise loss between the dense prediction and the Gaussian smoothed ground truth. Almost all previous works have followed this convention. Unfortunately, the performance of the resulting network is highly dependent on the quality of the Gaussian smoothed ground truth. However, it is non-trivial to set the right width for the Gaussian blob due to huge variations in human size and shape, irregular crowd distributions, and occlusion. We proved that imposing Gaussians hurts the generalization performance. The generalization error is no less than the absolute difference between the real ground truth and Gaussian smoothed ground truth gap and the empirical error. That is to say, when the empirical error is small enough, the better a model fits on the Gaussian smoothed ground truth, the poorer it's generalized to the real ground truth.
Recently, the Bayesian loss was proposed. This method transforms a binary ground truth annotation map into n smoothed ground truth density maps. Here, n is the counting number. Each smoothed ground truth density map Pi is the posterior probability of all pixels belonging to the ith annotated dot. However, when the loss is zero, the number of equations is less than the number of variables. Therefore, the Bayesian loss is underdetermined. This means that the predicted density map could be very different from the ground truth density map. In this work, we consider density maps as distributions and propose DM count for crowd counting. Our approach does not need any Gaussian to preprocess the ground truth annotations. We treat the predicted density map as a source distribution and the ground truth annotation as a target distribution. We use optimal transport to compute the distance between density maps. We present the generalization error bound of our method. The bound is tighter than that of the pixel-wise loss using Gaussian smoothed ground truth. We show state-of-the-art results on crowd counting datasets. Notably, we reduced the mean absolute error on the NWPU dataset from 105 to 88. Our method has three components. The first loss is the counting loss, which measures the difference between the predicted count and the ground truth count. The second loss is the optimal transport loss, which is based on optimal transport, OT. OT is the principled way to measure the distance between distributions. Here's an illustration of OT in a 1D case. Every point x in the source distribution mu will be moved to y in the target distribution nu, and the probability measure in the local neighborhood of x is equal to that of y. In this example, the area of the left yellow bin is equal to that of the right yellow bin. The objective of OT is to minimize the total moving cost, which is expressed in the primal form here. In this form, C is the transport cost matrix. Capital gamma is a set of all joint distributions whose marginals are mu and nu respectively. Gamma indicates how much mass should be transported from x to y, such that mu is transformed to nu. The dual form of OT is expressed below, where Cxiyj is the cost function between xi and yj. Alpha and beta are dual variables. We use the dual form of OT in DM count because the distributions are in the objective of the dual form, and the objective can provide gradient for the source distribution to update the network. As the total mass of the predicted density map and the ground truth density map are different, we first normalize both density maps, and then use the dual form of OT to compute the distance between these two normalized density maps. Alpha star and beta star are solutions of the dual form. In our experiments, we use the single-hole algorithm to approximate alpha star and beta star. As the convergence of a single-hole algorithm is slow, to stabilize OT computation, we include the total variation loss. The total variation loss is equivalent to half of the L1 distance between the two normalized density maps. The overall objective is a combination of these three losses, where lambda1 and lambda2 are tunable hyperparameters for the OT loss and the TV loss respectively. We show the generalization bound of DM count. As the number of data k increases, the expected risk using an empirical minimizer converges to the expected risk using the optimum minimizer. This bound is tighter than the generalization bound of the pixel-wise loss using Gaussian smooth ground truth, because the generalization bound of the pixel-wise loss has a positive constant term, which is the real ground truth and the Gaussian smooth ground truth gap that prevents its convergence.
We evaluated our method on 4 challenge datasets. On the largest dataset NWPU, our method reduced the mean absolute error by 17%, from 105 to 88. Here are results on all datasets. It is worth noting that our method achieves state-of-the-art performance using a simple VGG backbone. Here we visualize the predicted density maps from different methods. DM count is able to produce more accurate count. A closer look shows that density maps generated by DM count is much sharper, which results in high peak signal-to-noise ratio and structure similarity. Here's another example. DM count produces both accurate and sharper density maps. We visualize additional result by DM count on very dense crowd images. DM count works well on these images in terms of density map visualization and counting number. The loss in DM count is composed of 3 parts: the counting loss, OT loss, and TV loss. We study the contribution of each component. As shown in this figure, all 3 losses are essential to final performance. However, the OT loss is the most important component. Here, we investigate the effect of number of single-hole iterations in DM count. Using a small number of iterations lower the performance, which indicate that we obtain inaccurate OT solutions. When the number of iterations is greater than 100, DM count performance is state-of-the-art and stable. Crowd annotation is performed by placing a single dot on a person. Such process is ambiguous and could lead to inevitable annotation errors. We study how different loss functions perform with respect to annotation errors. We add random noise to the original annotation and train different models with the same noisy annotation. The proposed DM count is more robust to annotation errors compared to pixel-wise loss and Bayesian loss. Here we visualize 2 failure cases by DM count. These images either have poor illuminations or extremely dense crowds that are hard even for human observers. In summary, first we prove that imposing Gaussians to annotations hurts the generalization performance. Second, we propose DM count, which use optimal transport to measure the distance between predicted density maps and ground truth annotations. Theoretically, it has tighter generalization bound. Empirically, it outperforms other methods by a large margin. Thank you for listening. The code and pre-trained models are available.